A motorcyclist heading east through a small town accelerates at a constant 4 meters per second squared after he leaves the city limits. At time t equals 0, he is 5 meters east of the city limit signpost and he is moving east at 15 meters per second. We want to use some kind of coordinate system here, so let's set up an axis. That's the x direction, let's say. And 5 meters east of the city limit signpost, let's put that signpost at a coordinate of x equal to 0, because that's simple. That means that the motorcyclist is here at 5 meters. And we want to figure out things like what's the position and velocity at some later time. All right, given what's known, we know that the initial time is 0. That makes things nice and simple. The initial velocity is 15 meters per second. The acceleration is also given. 15 meters, 4.0 meters per second squared. We want to figure out what is the position and velocity at some later time. So we want to know what is x at some later time. What is the velocity at some later time? Oh, we did figure out what the initial position was. That was 5 meters. Okay. Given what what is known and given what we want, there's just some mathematical equations that we can use to figure this out. Those are called the kinematic equations. They assume that the acceleration is constant, which it is. Those equations look like this. X is equal to the initial position, x naught, plus the initial velocity times time, we call that v naught, and plus the correction that we have to include if there is acceleration. That is to say, if the velocity is changing. 1/2 times acceleration times the time squared. The velocity changes. It's equal to the initial velocity plus the term that tells you how much it changes by, acceleration times time. Lastly, because we might need it, there's a third equation you can derive from these two. It's often given. V squared is equal to v naught squared plus 2 acceleration, and then the change in x, the change in position. The final position minus the initial position, which you might see written as delta x. Okay? That equation is nice if you're not given the time and maybe you don't need the time, but you want to find an equation that relates position to velocity. In this problem, though, we're told what the time is. In part A, we're told that t is equal to 2.0 seconds. The position and velocity can be found right away by just taking these first two equations, plugging and chugging, and seeing what we get. So let's do that. The position is equal to the initial position of 5 meters, the initial velocity 15 meters per second times the time of 2 seconds, plus 1/2 the acceleration, 4 meters per second squared, and the time is squared. If we write out all these terms that we have, let's just make sure the units work out. 5 meters plus 30 meters over seconds times seconds. The seconds cancel. And the correction term to this, 1/2 of 4 is 2. 2 times 2 squared is 8. And that's meters per second squared times seconds squared, because everything in those parentheses gets squared. You see that the seconds go away, the seconds squareds go away. We end up with 5 plus 30 plus 8, which is 43 meters. We can do something similar for the velocity, but it's a little bit more straightforward, or a little bit easier. 15 meters per second plus the acceleration of 4 meters per second squared times the time of 2 seconds. 15 plus 8 is 23. The units had better be meters per second, and they are, because meters over seconds squared times seconds cancels 1 factor of seconds. Where is he when his speed is 25 meters per second? Notice they're not asking about time, and they're not giving the time. So we want to know what happens. Where is he when the speed is 25 meters per second? Given that all these things are known, v naught, the initial speed, initial velocity, I should say, it's 15 meters per second. The acceleration is known. And the initial position is known to be 5 meters. And we're trying to figure out what is x. That's what we want. It's worth pointing out we don't know what the time is, but we don't need it. They're not asking about it, and if we can get away with solving this problem without solving for the time, let's do it. The one equation that doesn't involve time is this kinematic equation. So let's try it, keeping in mind that what we really want is x, the position when this is going on. So before we plug in any numbers, let's do a little bit of algebra to isolate x, and then we can plug in the numbers at the end. So I'm switching to blue. If I subtract v0 from both sides, that's what I have. I'll divide both sides by 2a. The reason why I'm doing that is because then the 2a cancels from the top and the bottom. And I'm left with x minus x0. Lastly, I want to solve for x, so I'll simply add x0 to both sides of this equation, and that'll give me what I want. I'm ready to plug everything in. 25 meters per second, the whole thing gets squared, minus the initial speed squared, 15 meters per second squared, divided by 2 times the acceleration. And to that, I need to add 5 meters. Let you work out those numbers on your calculator. What you should find is that when you plug this all in, you get 55 meters, because on the top of that big fraction, you've got meters squared over seconds squared, divided by meters per second squared. Remember that that's equivalent to meters squared over seconds squared times seconds squared over meters. That's what you do when you have a fraction in the denominator. You can bring it up front, up top, as long as you take the inverse. The seconds squareds cancel. One factor of meters goes away. So your units here are meters. The acceleration is a function of time. We would draw it this way. Acceleration, units of meters per second squared. The acceleration is 4, or 4.0, and it's a constant. In other words, a graph that it should just be a horizontal line. Stays the same value for all time, at least while the motorcyclist is accelerating. The velocity, on the other hand, the velocity is changing. It starts off with some value and it gets bigger. So time on the horizontal axis and velocity in meters per second on the vertical axis. We know it begins at 15 meters per second and it steadily increases linearly. Something like this. Remember that the slope of the velocity graph is the acceleration. In other words, this thing is increasing at a rate of 4 meters per second each second. In other words, 4 meters per second squared. Lastly, making a plot of the position in meters as a function of time, we know that the position of the motorcyclist starts at 5 meters and he's initially moving. So the slope of this graph, which is the velocity, should not be 0. Not only that, but that slope should be steadily increasing. So the shape of this graph should get bigger and curve upward in such a way that the slope right here at the very beginning is equal to 15 meters per second, and that slope continues to get bigger as the time evolves.